My name is Fabrizio Ortu, and I work as a lecturer and researcher at the School of Chemistry, University of Leicester. And today I will talk to you about some of the research that I've done over the years as an F-block chemist. The title is a bit vague, but I think it gives a good idea of F-block chemistry as a whole. So the discipline itself, when it comes from the synthetic point of view, which is the one that I study, is very unconventional and a bit crazy at times. But the implications of the chemistry we do are very, very interesting because of the real-world problems that we try to tackle within this chemistry. When we talk about the F elements, we mean a family of elements that are separate in a periodic table, so they're not normally located in the main body of the periodic table, but they are at the bottom rather. And they're a group of 30 elements, going from element 57, lanthanum, to lutetium 71. These are the lanthanides. And then the actinides going from element 89 to actinium to element 103, lawrencium. Now, the lanthanides have a lot of applications, mostly because they have rather remarkable physical-chemical properties. In fact, they're used as lasers, they're used as bioimaging contrast agents, they're also used in catalysis, mostly as homogeneous catalyst. Or, for example, if you drive a Toyota hybrid, chances are, actually it's highly likely, that the catalytic converter contains cerium, element 58, for example. The actinides obviously are renowned for the applications for the military applications and for the energy industry. But both lanthanides and actinides are actually used a lot more than that. Just sometimes we don't know, but they are hidden around us. For example, if you have a phone in your pocket or in front of you, that phone almost certainly contains a magnetic material which is made of an alloy between neodymium and iron. And neodymium is element 60 in the lanthanide group. Or if you have a smoke alarm in your home, that smoke alarm will contain americium, element 95 in the actinide group. And what researchers have done over the years is develop a large body of fundamental research, both for lanthanides and actinides. And this is done in order to answer key scientific questions, because we want to improve on the technology that already exists and also find new applications if possible. The field that I specialize in is coordination and organometallic chemistry, which has been going around for a very long time, really. The first organometallic chemistry was developed in the 19th century. But this field has had a step change over the past 40 years, mostly because of many of the manipulation techniques that have been developed and some of the design criteria that have been developed by other researchers. A research field that I've been very interested in over the years is molecular magnetism. And I'll try and convince you now why we should care about this. This comes from a fairly simple problem, which comes from making our technological devices smaller and smaller and smaller, if anything more dense. The prediction of the miniaturization of technology comes from a law known as Moore's law. So the law predicted that the number of transistors in a circuit should double every 2 years. But then, in order to do this, we need to be able to make our transistors smaller. And this was the case for a while, but now we're reaching the saturation of this curve. And why is that? Well, the reason is that we are reaching the physical limit of the technology that we have. So we're not able to make these devices smaller and smaller. And the reason is that some of the properties of the materials, such as the heat capacity or the ability to dissipate heat, is working against us. So if we make the circuits smaller and smaller, these systems will stop operating. If anything, they will melt because they're able to dissipate the heat they generate. And this is the standard limitation of the top-down approach. But why do we need to do this? Well, we're not just stopping technology. We're not stopping technological advances just because we cannot make our devices smaller. So the information that we generate keeps on growing regardless of what the industry does. And it's growing by 40% every year. And the increasing density of our devices is not keeping up with this growth. In fact, it's increasing by less than 10% per year, and also it's plateauing now. It's almost reaching the limit, as we said. The actual technological limit, as predicted, is around 10 nanometers. So current magnetic materials average 20 nanometers in terms of grain size, and it's predicted that we can shrink them down to 10 nanometers, which will give us a density limit of around 6 terabytes per square inch. But how about if we reverse our top-down approach and we do a bottom-up approach rather? In order to do this, we need to manipulate the smallest entities, which are atoms and molecules. So that's what we do as chemists. We just operate on the on positioning atoms in a certain arrangement with respect to each other and make interesting molecules. So if we made one of these interesting molecules that has the properties of a magnetic material, then we would have made a very, very small magnetic device. And that's the idea behind single molecule magnets, or SMMs. So the first SMM was reported in the early 90s, but it displayed magnetic properties only at minus 269 degrees, which makes it pretty much useless for real-world applications. So we need to try and make them be better, but at least it means that in principle they work. So, and that's a good point where to start. So this molecule, just if you flatten on 2D, is roughly 2 nanometers wide, which gives us, if you do in terms of surface, around, so this molecule will be our single bit, essentially. So it gives us 1 bit per square nanometers, which gives us 6.2 times 10 to the minus 3 squared inch per terabyte. So if we put that in terms of potential density per square inch, it gives us 160 terabytes per square inch. So we went from 6 to 160. So if we're able to do this, then we can, essentially we can become really rich by selling this technology. But there's some problems. As I said before, these molecules don't operate at high temperatures. They actually stop working completely. And we need to approach at least liquid nitrogen temperature in order to make them feasible for real-world economy. And that temperature is minus 196 degrees. There are various reasons why. So, first of all, nitrogen is very available as a cooling agent. It's a lot cheaper than helium. And it would actually allow not necessarily household applications, but companies and private sector could definitely use it. So it could be used by Google in their servers, for example. So the target for a synthetic chemist is to develop molecules that have a much better, they're much better in retaining these magnetic properties at high temperatures. The molecules the atoms that are the best candidates for this type of applications are the lanthanides. And the reason is that they have incredible magnetic properties. They are connected to their special position in the periodic table. When you talk to a physicist, they can always approximate things to a sphere or something along those lines. And this is a picture of a lanthanide element, dysprosium, in its most magnetic state. Now, there's a lot of there are many equations behind this picture, but what the physicists provided us was a design criteria that told us dysprosium has electron distributed around the nucleus in this specific way. And in order to stabilize the most magnetic state, you need to put things, or atoms, or ligands, in an axial coordination field, so at the top and the bottom. And this is something that a coordination chemist like myself can do, because we know the behavior of these individual elements, and we can try to arrange them in a very specific way. What they predicted was that if we could put these elements, so dysprosium in the middle and ligands in an axial coordination field, we could have molecules that retain magnetization at very high temperatures, which will make all of a sudden these applications very feasible. So the ball was back into our court, so we had to try and come out with a strategy where we put a metal in the middle and 2 ligands at the top and the bottom. Okay, so back to the lab, and this is what we did. We took dysprosium with 2 very large aromatic rings at the top and the bottom, 2 cyclopentadiene substituted ligands, and then you can see the molecule on the left has a chlorine in the equatorial position. So we found a way to remove that chlorine, and what we obtained was something sort of close to the picture they gave us. See the dysprosium in the middle and only 2 ligands at the top or the bottom. And the physicists were right. The molecule that we had magnetization up to minus 213 degrees centigrade, which is still very, very cold, but it's a massive improvement compared to where we were before, which was minus 260 degrees. And we're not too far from the magic threshold of minus 196 degrees, which is the liquid nitrogen cooling temperature. So by using molecular design, we vastly improved the performances of this SMM. And now we started studying why these performances are so much better, which triggered a whole other research field, which is done more on the theoretical side. And also we made a lot more molecules analogous to this dysprosium molecule to try and make us understand a bit better the relaxation mechanisms. Also, like, just to conclude briefly, not only F elements are very fun to use, it gives an idea of how research like this can really address real world problems. And also from the more personal point of view, other than the intellectual satisfaction in a way, is the fact that I got to work with some amazing people from all around the world and create some great interactions. Some of these will be friends for life. So it's been like really a great experience working in this research field. If you want to know more, you can visit my website, which is orturesearch.com, or just drop me an email if you want to know more about my research. Happy to chat anytime.